going to start with the 613 warm-up, so if you can go ahead and turn probably page 2 or 3. We've got rigid and non-rigid transformations. And so rigid would be the kind where you just shift horizontally and vertically. Dilation is a non-rigid transformation. So write a new equation with the given transformations, then sketch the new parent function on the same graph as the parent. Parent's already provided on every graph. So we've got 1 through 4 here. So this is number 1 with x squared. I'm not going to do this one. This is 1 over x, which we learned in unit 4. I'm not going to do this one either. We get a shift right, a shift right, and a shift up, and a dilation of -1, which means it has been reflected. So we can figure out with that one. And then we've got the square root function. No vertical shift, but a horizontal shift and a dilation. And then we are going to do number 4. Just very quickly with the dilation, make sure that the best thing to do is to take the outputs at each point and times them by the dilation factor. So we've got our dilation, which is 3, or our amplitude of this one has become 3. It's been shifted vertically 1 unit and horizontally pi halves. And since this is pi, this must be pi halves right there. So this is my shift. Pi halves is where 0 is going to be, except for that it's been shifted up 1. So it's actually right there at pi halves. That's our midline. That's our shift up for our midline. It's got an amplitude, so it's right here. And then half a unit over, it's going to go up 3, then down, down, up, down, down, up, mid, down, up. And so this is our graph. It looks like a flipped over cosine graph. Your equation should be terms. We're going to use sine. So we've got 3 sine of x, that's our amplitude, plus 1, that's our, and the horizontal shift goes in here. There's been no change in the period on this one. So I've got x and pi halves. Since it's been shifted, I went right. I did that wrong. That's been shifted. Let's shift this whole thing. So that would be not shifted, and that's left. So this just actually looks like a cosine graph. Excuse me for not reading carefully. And so there's my graph. So anyway, it's been shifted left, and left is plus, is minus, plus, or left. My domain is all real numbers, or negative infinity to infinity. My range is from -2 to +4, and the 4 and the 2 are included. Or you can write -2 is less than or equal to y, which is less than or equal to 4. And so that's our domain and range. Good luck on the others, and back it up, pause it. I'm not going to give the answers. I can tell them to you in class. Take a look at what else is there and do the other 3. So I've done the new one. All right. For those of you who were in class on Friday, this is a recap. So you don't need to take very good notes, but if you were not in class on Friday, we're going to get started with what we were talking about. So we're moving into defining what tangent is. Tangent we know is opposite over adjacent. We're going to find the degree of any angle of rotation, either in degrees or radians. Explain why your definition is reasonable. And then we're going to put it on the unit circle next. And I actually think the unit circle is a little easier to do. We've got our point here on our circle, x, y. And we know that on the unit circle, it's cosine of x, cosine of theta times the sine of theta on the unit circle. And so, since we know that it's opposite over adjacent, and that's x and y, we've got the tangent of theta is equal to the opposite side, y, over the adjacent side x. The other thing to think about going back up here is that tangent of theta we know is opposite over adjacent, but we also know that it's sine over cosine. So sine of theta over cosine theta. And we know that sine is y over r, and cosine is x over r. And when we multiply those complex fractions to simplify out, so we multiply by the reciprocal, we get y over x that way. The other way to think about this is opposite over adjacent. So we know that opposite over hypotenuse and adjacent over hypotenuse. And so the hypotenuses would cancel out just like the radius did here. So you'll notice the radius is not in our tangent definition, unlike with both sine and cosine where the radius comes into play. It doesn't matter what the radius is for tangent. It disappears. The radius has nothing to do with the tangent of an angle. All right. So also on Friday, we talked about some of our standard definitions, because we know that this length here represents the cosine, the sine of x, sine of theta, excuse me, and this is the cosine of theta, or in other words, AC. AC is the cosine of theta, and BC is the sine of theta, and AB is 1. So indicate on the following diagram which of the line segments represents these. There's also a line segment we can use. So this is the unit circle triangle that we've spent a lot of time with. This is the y value. This is the x value. But there's also a length for tangent. And so here's what we're going to be dealing with our picture for tangent. And we're going to play some games. And this is where it gets a little tricky. It's not hard. It's just a little strange. And so we're going to see what can be done here. And see if we can come up with what's going on. And I will need that in a moment. So we know that if this is theta, that if we were using our triangle, the tangent of theta is equal to the sine of theta is equal to BC over AC. And what we're trying to show is that DE is going to represent the tangent of theta. That's our goal. And so what we're looking at here is this pretty straightforward statement. And tangent of theta is opposite over adjacent. So using the other triangle, with the still same angle theta, it's DE over AE, and AE is the radius of the circle, or 1. So tangent of theta is equal to DE. This just comes straight out. Or in other words, since we know it's sine over cosine, BC over AC, that works out there. And it works out here too. So that is a pretty straightforward situation. And you need some words to go with this. So some of the words that I was saying would be helpful. The fact that it's the same angle, opposite and adjacent, is where these both came from. So we know that DE is equal to BC divided by AC, or the tangent of theta. That's the other two things. So those are kind of the ideas, and that's pretty much what we did on Friday. And then we started talking about how to graph. So this is new. We started talking about how to graph. And since the key here for graphing is that understanding that tangent of theta is sine over cosine, and some basic playing with the unit circle. And so the tangent of theta is sine of theta over cosine of theta. And notice that what we did on Friday is we took a quick trip to Desmos and graphed it really quickly. I want you to go ahead and do that. If you haven't already, just take a quick look and you'll notice a lot of asymptotes. So there's a lot of asymptotes in this because cosine is 0 regularly. So anytime the cosine is 0, the tangent of theta has an asymptote. So we need to figure out where the asymptotes are first. So this is going to take us some time. So I'm going to put the graph in the next video. So I'll talk to you in a little bit. about the graph of tangent of theta.